Assalamualaikum warahmatullahi wabarakatuh, and selamat sejahtera to all participants of Simposium Kebangsaan Sains Matematik ke-28. My name is Nur Haniza Sarmin from University Technology Malaysia. I want to share my research today titled Seidel Energy for Cayley Graphs Associated to Dihedral Group. This is my joint work with my PhD student Amira Fadina and Professor Ahmad Irfanian from Firdausi University of Mashhad. My presentation outline is as below. First, I will introduce what is the energy of a graph, the Seidel energy of a graph, what is a Cayley graph associated to groups, motivation of this research, some literature review, preliminary results, and I will share some results on the Seidel energy of Cayley graph associated to the Dihedral Group. Conclusion, future work, and acknowledgement. Now, as an introduction, what is actually the energy of a graph? The energy of a graph is an invariant that is calculated from the eigenvalues of the adjacency matrix of a graph. And the energy of a graph is given in this symbol, a summation of the absolute value of these eigenvalues. And what is actually the adjacency matrix of a graph? So if we have a graph with vertices and edges, and the adjacency matrix is denoted as A to be n by n matrix, and the rows and columns are indexed by the vertices. So if I is not J, then the ij entry is 0 if the vertices are non-adjacent, and the ij entry is 1 if they are adjacent. The ii entry or the diagonal entries is 0 for I from 1 to n. And sometimes we just call the adjacency matrix as A. So as an example, let gamma be this complete bipartite graph K33, in which the vertices are 1, 2, 3, 4, 5, and 6. So the adjacency matrix of gamma, which is A gamma, is given in the following. So we have this label for the rows and vertices as the vertices 1, 2, 3, 4, 5, 6, and the diagonal are all 0. You see that there is an edge from 1 to 4, 5, and 6. So from 1 to 4, 5, and 6, you see all the ones, and 1 is not connected to 2 or 3. So from 1 to 2 and 3 are 0, and likewise. So this is also, you can see that a symmetry matrix. And by this adjacency matrix of gamma, we can find the characteristic polynomial as given in our linear algebra. So the f of gamma is determinant of A minus lambda I. So we calculate the determinant of this matrix, turns out to be lambda to the 6 minus 9 lambda to the 4. And by equating this to 0, we can actually factor this and see that equating this to 0 gives us lambda I is 0 with multiplicity 4 and plus or minus 3 with multiplicity 1. And thus the energy is just the sum of this absolute value of these eigenvalues, the sum of 4 with 1 times 3 and 1 times negative 3. So this is a typo here. It's just the sum of this. So it's equal to 6. And what is the Seidel energy of a graph? So the Seidel energy of a graph is the sum of the absolute value of the eigenvalues of the Seidel matrix. And Seidel matrix is a little bit different than the adjacency matrix, in which that Seidel matrix of simple graph gamma with n vertices and m edges we denote as S is a real square symmetric matrix of order n, defined as if they are adjacent is equal to -1, and if they are not adjacent is equal to 1, and again the diagonal is equal to 0. So for this complete bipartite graph K33, the Seidel matrix S gamma is given in the following. So we still have 1, 2, 3, 4, 5, 6 as the vertices, and you see 1 is connected to 4, 5, and 6. We put them -1. 1 is not connected to 2 and 3, so we put them as 1. And the diagonal are all 0. So for this Seidel matrix, we can compute the characteristic polynomial as before, and turns out to be factored to theta minus 5, theta plus 1 to the 5. So the Seidel eigenvalues is equal to -1 with multiplicity 5 and 5 with multiplicity 1. Then we sum up all this and turns out that this is equal to 10. The Cayley graph of a group is introduced to explain the algebraic structures of abstract groups, which are described by set of generators. So this Cayley graph, depending on the specific set of generators, we denote as gamma, CAY, Cayley, GS, where G is a finite group, S is a subset of G, which does not contain the identity, and in which S is equal to the S inverse. Our vertices is all element of G, and we have these edges in between GI and HI if HI is equal to SGI, in which S is in S. So this is how we determine that two vertices are connected. So as an example, we let that D6 is the dihedral group of order 6, and this SB, AB, and A squared B is the generating subset of D6. Then the Cayley graph of D6 with respect to this generating subset is this have vertex set of all elements of D6, 1, A squared, B, AB, and A squared B, and we check whether they're adjacent. Like 1 is adjacent to all elements in S, B, AB, A squared B, and some others are adjacent. So we check one by one, and you can see as the definition before that two vertices are connected if one is S times the other one. And our focus in the whole research is for this particular scope is in the Dihedral group, in which it's an element of rotation and reflection of order 2n, and this is the presentation of the Dihedral group generated by A and B, and we have this rotation and reflection. So the motivation comes from the general form of the structure of the Cayley graph associated to groups that can help others to easily find the energy of the graph that have the same group and the graph properties. And in chemical graph theory, the computation of the energy of graph can be corresponded to molecular structures where the bonding of atoms are presented as simple graph in mathematics. The generalization of the formula can help chemists to calculate the energy of the molecular structures in a much simpler way in future, plus it is more time and cost saving. And in medical, the methodology of the energy of graph is used in the search for the genetic cause of Alzheimer's disease, AD, by understanding the network breakdown in AD, where the cortical disconnection were examined based on the energy of the graph and its spectrum. So as an example, imagine we have this biophenylene conjugated hydrocarbon atom skeleton, in which we represent this by this graph, and this graph corresponds to this molecular structure. We can calculate and get the energy, and then we approximate the energy. And the chemists did this in other way, which is more costly. So from this molecular structure, we transform in mathematical modeling as a graph, we find the matrix, and we calculate, and we get the energy. So this is the motivation of the research. Some research that have done on the energy of graph. So Huckel in 1930 started this proposed Huckel molecular orbital theory that used by chemists in approximating the energies related with pi electron orbitals in conjugated hydrocarbon. Later, Gunther and Primus used the fact that the Huckel method is using the first degree polynomial of this matrix, and they realized this, that they can use for certain graph. Gutmann in 1978 defined this energy, as I mentioned earlier, to be the sum of the absolute value of the eigenvalues. Zhou in 2008 studied the relation between the main eigenvalues and eigenvectors of an agency matrix of the graph finding the ordinary energy, then the Seidel matrix of the graph used in finding the Seidel energy of the graph. And he found that these eigenvalues of the Seidel matrix associated to the orthonormal eigenvectors, and he had this theorem that the eigenvalues are precisely the main eigenvalues of the Seidel matrix. And if you have one eigenvector corresponding to eigenvalues of M, then the sum of the Bj alpha j is an eigenvector of the Seidel matrix corresponding to mu. And this corollary helped us in proving and getting some of our results. If you have these main eigenvalues of the ordinary matrix, agency matrix, and also the Seidel matrix, then we have this formula that the sum of 2 lambda I plus theta I is just equal to n minus L. Other authors that done research on Cayley graph related to groups included first by Arthur Cayley, of course. He explained the idea of abstract group that described by the set of generators. Varan et al. Analyzed the symmetries in the interconnection network of a variety of Cayley graph or permutation groups. Konstantinova surveyed the historical changes of some problems on Cayley graph, such as the Hamiltonicity and diameter problems. Adiga and Ariamesh determined the number of undirected Cayley graph of symmetric group and alternating group up to isomorphism. So these are just sharing some preliminary results that we'll use later in our research to find the spectrum of the n-cycle graph. So the spectrum of the n-cycle graph Cn consists of this number 2 cosine 2 pi j over n. For the complete graph Kn, the Seidel spectrum is found to be 1 minus n and 1 with different multiplicity. And for complete bipartite graph, the Seidel spectrum is 1 minus n with multiplicity 1 and 1 with multiplicity n minus 1. Later on in 2018, we found these results for Dihedral group in which S is this subset of the Dihedral group. We found that for the Cayley graph, the Cayley graph of this are cycle graph n over 2 C4. And so we get this spectrum of this graph and also the energy. And later on, we found for the case in the Dihedral group and with the generating subset S, not only the S of certain order, but for this generating set, we found the Cayley graph to be complete bipartite. And also we found the spectrum to be of multiplicity 0 with multiplicity to n minus 2 and plus or minus n with multiplicity 1, and also the energy of the Cayley graph. So this gives us the result of our Seidel energy of Cayley graph for the Dihedral group, and it turns out that the Seidel eigenvalues is plus or minus 1 with multiplicity n. For the Seidel energy for the Dihedral group with subset of order 1 turns out to be 2n. For the subset of order 2, the Seidel energy turns out to be the summation of 8 cosine 2 pi I over n. For the subset of order 2, again with this form, this is how we prove it. And this is how we get the Seidel energy. The next case is when the set S is of order 2 with this form, and this is the Seidel energy of the Cayley graph. Okay, and for this type, the Seidel energy of the Cayley graph turns out to be this form. This is the result for this particular set S. And when we have of this type and n is even, we get this result for the Seidel energy. And when S is a generating subset and generating set, we have this for n minus 2. So we can extend to the higher order of the subset and future researchers can find this for other types of groups, new types of energy can be done, and we can do this in computer engineering field also. So we would like to express our appreciation for our grants, and thank you.